So now we reviewed the questions about basically Bernoulli's equation, which is used in terms of garden watering in the book. The first question says a 2-inch diameter pipe carries water moving 10 centimeters a second. The pipe suddenly narrows down to a 1/2-inch diameter pipe. Which of the following statements is true? The water in the 1/2-inch pipe moves at a higher speed and the pressure is higher than in the 2-inch pipe. The water in the 1/2-inch pipe moves slow at a lower speed and the pressure is lower. The water in the 1/2-inch pipe is at a lower speed and the pressure is higher. The water in the 1/2-inch pipe moves at a higher speed and the pressure is lower. So it basically looks at both the speed in the 1/2-inch pipe and also the pressure there. Again, the idea is that the picture in your head should be that what you have is that you have a 2-inch pipe that suddenly narrows down to a 1/2-inch pipe. And what you know essentially is that the flow speed in the 1/2-inch pipe has to be higher than in the 2-inch pipe because whatever water is incompressible. So whatever water goes into the big pipe has to come out the small pipe. And so as a result, the velocity has to be much higher for the water going through the small pipe. So that allows you to eliminate it. So the 1/2-inch pipe, the water moves at a higher speed, and so that allows you to eliminate the two possibilities where they're at a lower speed. So the question is, well, what happens to the pressure? And this is where Bernoulli's equation comes in. Remember, Bernoulli's equation, essentially what it does is it's measuring conservation of energy. And so it's measuring the kinetic energy, and so you have a term that looks like the 1/2 mv squared, except its density. This is the kinetic energy per unit volume, essentially. And then you have a term, actually, that shouldn't put that there. Also have a term which is the potential energy, which basically just looks at its height above the ground. And the idea is that in the left pipe, which is the bigger pipe, you have the pressure plus the kinetic energy plus the potential energy. And on the right pipe, essentially, you've got essentially the same thing. Now, the idea, of course, is the height doesn't change. Okay, and so these terms are equal to each other. You can kind of ignore it. But the point is in the small pipe, the kinetic energy has to increase, and so in order to make these terms equal to each other, the only thing that can really change is that the pressure has to go down. And so the point is if these two, the pressure has to be lower. In other words, the speed is at a higher speed, and the pressure is lower, and so that's what it has to be. Now let's look at the next one. As water flows steadily up a uniform diameter pipe inside a skyscraper, it converts its kinetic energy into gravitational potential energy, gravitational potential energy into pressure potential energy, pressure potential energy into gravitational potential energy, or pressure potential energy into kinetic energy. And really what's happening here is you have some skyscraper here, and you've got a water pipe coming in on this side, and the idea is it goes up. Now the idea is that the kinetic energy can't really change because if assuming the pipe's this constant diameter, the velocity going in is equal to the velocity as it goes up the pipe, and so the kinetic energy doesn't change. But what does change is down here you've got kinetic energy and you've got potential energy. And the idea is here basically the potential energy is low, and so the pressure has to be high. And so as it goes up, what happens is, since the kinetic energy can't change really, as the potential energy increases, that means the pressure has to naturally go down. So the highest pressure occurs basically at the base. And this makes sense because you've got to support the entire weight column of water which goes up the skyscraper. So the idea here is that the pressure potential energy basically has to be converted into gravitational potential energy as it goes up. So in other words, as the potential energy increases, then the pressure has to decrease in order to compensate. And it can't change the kinetic energy, so that goes away. And it doesn't convert gravitational into pressure potential as it goes up anyway. And it doesn't convert kinetic energy into gravitational potential. Otherwise, that would mean that the water flow is slowing. So this is the idea. It's basically pressure and gravitational potential. Let's do the next one. Firefighters are battling a fire on the 10th floor of an apartment building. When they stand on the ground, their fire hose can only shoot water up to the 8th floor. So they get the bright idea of carrying the end of the same hose up a 2-story tall ladder and shoot the water skyward. Now the water rises up to, and the idea is essentially that if it had water flow through the water, through the hose. And the idea is that Bernoulli's equation works, right? So yeah, you've got a large pressure and water's flowing through it. But the idea is that when it gets out to here, it only has enough energy to get up to the 8th floor. And so it's never going to have any more energy than that, even if you bring the hose up to a 2-story tall ladder. It never is going to have enough energy to get all the way up to the 10th floor. And so even if you go up a 2-story ladder, it still will only get up to the 8th floor. It doesn't get up to the 10th floor, 9th floor, and it certainly, it should be able to get up to the 8th floor. So again, it's Bernoulli's equation. It's just conservation of energy. Water arrives at a house at ground level through a wide pipe. The plumbing then carries that water directly to a shower on the ground floor, upward to a shower on the 2nd floor, and downward to a shower in the basement. The spray from the 3 showers is strongest in the basement, strongest on the 2nd floor, strongest on the ground floor, equally strong on all floors. And it's Bernoulli's equation in action. So the idea is that you have water coming into the house, and you've got a shower on the 2nd floor, the 1st floor, and down the basement. And the idea is, as you go through here, what's changing, essentially, is not the kinetic energy, but what is changing is that as you go up the house, this potential energy term increases, and so as you go up the house, then the pressure has to decrease. So you get the weakest pressure coming out of the shower faucet at the top floor, and it's strongest down at the bottom floor because that's where the pressure is highest. And again, it's supporting this whole column of water going up the house, and so the pressure has to be, it's like being at the bottom of a pool, is the pressure has to be largest down at the bottom. So it's strongest in the basement, and it's clearly not strongest on the 2nd floor. And it's clearly not equally strong on all floors because that would violate conservation of energy. So that's the idea. I think that covers it all.